All right, welcome. This is going to be a very introductory video just to get some things out in the open before we move on to some more advanced things. Chapter 3, we're going to start talking about the notion of random variables. So we'll start out with definition 3.1 of their text here. A random variable. A random variable, which I'll often denote capital R, capital V. We'll be using random variables frequently from here on out. Random variable is a function. That associates a real number with each element, in the sample space. With each element in the sample space. Okay. Remember what it means to be a function. A function in English, loosely just saying, right, one input gives you one and only one output. So a random variable is a function associates your real number with each element in the sample space. Some common conventions are that capital letters will denote the random variable. Capital letters. So maybe capital X, capital Y, or capital Z, for example, will denote the random variable. And you'll see we will use those letters frequently. And it sort of starts to take on the look of just another variable, which kind of helps explain the nomenclature a little bit. So capital letters will denote the random variable. Its corresponding lowercase letter, so little x, little y, or little z, would denote one of its values. All right, so let's take a look at an example here of some random variable before we go any further to kind of help clarify some of the notation. Let's say that 3 coins are tossed simultaneously. Got 3 quarters, and you throw them up in the air. 3 quarters are tossed simultaneously. So at the same time. All right, so capital X will denote the number of heads. Capital X is the random variable that will denote the number of heads. So let's take a look at this. Let's write out the sample space. Three coins are tossed simultaneously. So let's just go ahead and take the time to write this out. You could get heads, heads, or heads. You could get heads, heads, or tails. You could get heads, tails, and tails. Heads, tails, and heads. Let's see, we could have a tails first, and then heads. 2 tails, so you could have tails, heads, and tails. Or tails, tails, and heads. Or 3 tails could come up. Alright, so then let's just look at what would be the value little x associated with each of these elements in the sample space. Well, capital X is denoting the number of heads. So this would be when this would take on the value 3. There's 2 heads here. There's 1 of them there. There's 2 of them there. There's 2 heads there. 1 head here, 1 head here, and 0 in that case. 0 in that case. 0 in that case. All right. That looks 6. Good. All right. Just some introductory stuff here. A couple more definitions on this. Definition 3.2. We've talked about sample spaces, but we're now going to talk about some specific types of sample spaces. And specifically, we want to define what a discrete sample space is. A discrete sample space contains a finite number of elements. This is a finite number of elements or an unending sequence. Unending, that's not how you spell unending. Unending, let's try that again. Unending sequence. Unending sequence with as many elements as there are whole numbers. And we'll take a look at an example to maybe try to help clarify this sort of last part of this. Because it's typically a discrete sample space. We'll commonly deal with finite ones. That's a specific quantity that is in your sample space, right? For example, this sample space above in coins, that's discrete. There are 8 elements there. That's a finite number of elements in your sample space. It is possible to have an infinite number of elements in a discrete sample space. But it's not just any type of infinity. It's an unending sequence in the sense that there's a way to list them out, if you will. Okay. So, for example, an example of that, consider the experiment where you throw a die, let's say until a 5 occurs. Until a 5 occurs. Right, so you got a standard 6-sided die, and you're just going to keep rolling it until you get a 5. All right. So here, S, the sample space, is an infinite discrete sample space. Is an infinite discrete sample space. Infinite discrete sample space. All right. This is discrete because we can list out the elements, but it's infinite because it's possible that you could be rolling this die indefinitely until you get a 5, right? It's unlikely, and eventually we'll talk about how to compute these probabilities. It's unlikely that you have to roll the die 100 times to get your first 5, but there is a small chance that has a possibility, right? So if I'm going to say, just let capital F mean I get a 5, and N would be that the result of rolling a die is not a 5, then our sample space S, well, it'll look like this. One element is you get a 5 in the first try. Throw a die until a 5 occurs, so then you would stop. A second element is that it takes 2 tries. That would be not a 5 and then a 5. Third element is it takes 3 tries. No, a 5, not a 5, and a 5. Right? Not a 5, not a 5, not a 5, and a 5. And you can keep listing this on forever. This is an infinite discrete sample space. Okay? Infinite discrete sample space. The more common type of infinite sample space that you might be thinking about is a continuous sample space. And maybe once we write this out and compare and contrast, that'll help clear up this infinite discrete case as we compare it to the continuous type. A continuous sample space. Continuous sample space contains an infinite number of possibilities. Infinite number of possibilities equal to the number of points on a line segment. Equal to the number of points on a line segment equal to the number of points on a line segment. So for example, of a continuous sample space, let's say X is the proportion of people. X is maybe the proportion of people who respond to a survey. In this sense, then we would say X is continuous. If it's a proportion here, this is continuous, and this is bounded between 0 and 1. Bounded between 0 and 1 in the sense that you could have any proportion. You could maybe get 60% response rate. You could maybe get 60.1% response rate. You could get a 60.11 or 60.15 or a 60.0110111%, yada, 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 right? Continuous sample space, right? If you were to take any two sample points that you pick on there, you can always squeeze one in between here, right? Unlike this discrete sample space, there's nothing between this element and this element, right? There's no 2.5 tries. It's either 2 or 3 or 4 or 5, right? That's discrete. In a continuous, you can always put something in between, right? Let's say that X is the waiting time in minutes. Waiting time in minutes in line at, let's say, the bank with, let X be the waiting time in minutes in line at the bank. Okay, so then X would be a continuous random variable. The sample space is continuous. Capital X is continuous, and I'll often abbreviate continuous CTS with X greater than or equal to 0. Theoretically, right? Because you could potentially be waiting in line forever, right? You could be waiting in line 5 minutes or 6 minutes or 5.5 minutes or 5 minutes and 31 seconds or 5 minutes and 30.5 seconds. It's continuous. That is continuous, okay? It is infinite, right? Both of these cases are infinite. Notice that this case is infinite. Also in the sense that X can go on up to infinity. This is infinite as well, even though it's bounded between 0 and 1. There are an infinite number of numbers in the real number line between 0 and 1. Even though it's bounded, it's still infinite, okay? Just some introductory concepts there. We're going to dive more deeply then into discrete things in a specific section, and then we'll dive more deeply into continuous things in later sections as well. So for that, we will see you in another video.